All right, so till now we have seen module 1 and module 2, where we have discussed about the significance of measurements, why measurements are important, and we have also discussed about various sensors that are used, or the principles that are behind various sensors, and that are obviously useful in the measurement process, measurement of various physical quantities. So though that is not the enough, or that's not all about the sensors. Actually, there are many sensors that we have not gone through, or there are many sensors that are there, which exist in kind of a lot of industries, like maybe hospital industry, you can say, or any other industry. But obviously, the any course is actually the purpose of every course is actually to give you the introduction and to tell you about the physical principle, about the basic physics that is involved, and the basic science that is actually involved, and how basically you can design new sensors, how do you identify the need, and how do you basically go about designing those systems. So I think what we have covered till now is enough in terms of different types of physical principles used in the sensors, and also the measurement systems, and about the instruments types and other things. Now, this today's lecture is actually about the module 2 only. We'll finish module 2 today, and from tomorrow, day after tomorrow, we will start with module 3, which is about motion and, you can say, force measurements. So we'll be specifically covering some of the techniques, some of the sensors in detail, in force and motion measurement, and also in temperature and pressure measurement. Okay, so that would follow as per my that list of topics that I have already put up with you. So this analog to digital and digital to analog conversion, this is more specifically, if you say, it's more about an electronics topic in electronics. But as a mechanical engineer, obviously we don't need to go deeper into it, but it's very important for us as an engineer of or can say as a student of mechatronics or measurement systems, or instrumentation system course, that we should be aware about what's actually going to, how basically these things are designed, and what actually goes into it, rather than going deeper actually into these things, because there is a huge resource available for analog to digital and digital to analog conversion, issues with analog to digital convergence and other things. But that's not the scope of this course, let's say. So we'll be restricting ourselves to basics of analog to digital and digital to analog conversion. All right, so what we know about analog signals is that they are the signals that vary continuously in time. So analog signals are the signals that are continuously varying in time. Whereas digital signals is the signal, or the information, you can say, at a particular instant of time only. Now, the examples of analog signals are, can say, a simple AC main signal that we see, which is nothing but a sinusoidal signal with, let's say, some frequency called 50 hertz and maybe some amplitude. All right, let's check this. All right, so the AC signal that we get in our mains is actually the sinusoidal signal, which is an analog signal that varies continuously with time, and also obviously it has some amplitude and frequency. Another example is of the another example could be of the stress strain relation. Generally in mechanical systems we see, or mechanical components, this is also analog. So just to maybe show it in the form of a graph, an amplitude versus time graph. So this is the, let's say, AC signal. This is the amplitude. You can see the voltage here, and this is the time. All right. So this is analog. Similarly, we have the stress strain relation of some elastic or semi-elastic members. You have the force versus time. So this is also analog in nature. Another example could be pressure variation associated with the transmission of human voice through air. So all these are typical examples of analog signals. All the sensors that we generally use, that we have discussed till now, for example, ultrasonic sensors, or you can say Hall effect. Maybe Hall effect is a little digital in nature, but there are, let's say, piezo, or you can talk about in the strain gauge, piezo resistive, and many other sensors that we generally see usually key out the output as the analog output. So we have a signal, or we have an output that continuously varies with time. Okay. Now, why do we need to convert them to digital? Let's say in the first instance, because the answer is quite clear. Because with digital, the most important thing is that we can control things well. Because when we are talking about sensors, sensors are used to basically measure the physical quantity. You can say measurement is the basic purpose, and when measurement is the basic purpose, we have seen in measurements also that we would like to actually control the parameters. Okay, so for effective control we need to have good sensors, and so obviously for control we would like to have some digital device like a microcontroller or a microprocessor or any other, or you can say a computer itself can be used actually, in those cases where we connect the output of the sensor to the microcontroller, and that is that puts up some control command back to the plant. All right. So it's very important for us, because the microcontrollers that we generally use are very popular actually in the control of these, all these systems that we generally employ in the industries, or let's say in our day-to-day life. So that's why we need to convert these analog signals from the sensors to the digital, because microcontroller is a digital device. So this analog to digital conversion is very necessary. And on the other hand, we do have some let's say sensors. Maybe you just talked about Hall effect sensor, or you have some encoders, optical encoders, maybe some other example also, which have directly a digital output. So they directly give you a digital signal. So those types of sensors you generally do not require analog to digital conversion, because it's already a digital signal, so it can directly be interfaced to the microcontroller. All right. So now how do we do this? Because microcontroller obviously is a digital device, and we know that digital device generally operate at very low voltages. What is the principle that is employed in the conversion from analog to digital? And sometimes again we may have a digital output from the microcontroller, for example, again microcontroller, and it obviously we have fed, let's say, a digital input to this by doing something called as analog to digital conversion. But then maybe the plant again is an analog, or you can say a continuous system. So obviously you would need to do something called as, because the output from the microcontroller will be digital, so you need to do something called as digital to analog conversion back, because this does not understand these digital signals. So this needs to be fed with an analog signal, which is, let's say, an actuator requires an actuation signal in terms of some voltage. So obviously it would need some digital to analog conversion. So all these processes, analog to digital and digital to analog conversions, are actually required because we are employing a microcontroller. So now what is a digital signal? Digital signal actually is a signal that consists of some, let's say, a signal of this form, which means it has some high state and a low state, again a high state and a low state, which is typically represented in the form of ones and zeros. So we have a signal like 1 0 1 0 1 0 1 0 and so on. Now, so I'm getting disturbed with these uh, all these things that's coming up. So we have a logic 0 and logic 1 that we generally use in digital circuits. So we don't have any other thing. We have just logic bits 0 and 1 that controls the whole, let's say, whole signal. So this is the level and this is the time. All right. Now, why do we, again, another question could be, why do we go for digital, methods, or you can say, why do we go for digital, maybe digital methods, we can say, or why do we use digital signals? Why not directly analog signals? The reasons could be listed here. The advantages of digital methods. So the advantages of digital methods are, I can say, the features. The digital electronic components are generally easier to design. And fabricate than analog ones. So this is similar to what we have talked about, even the analog filters and the digital filters. Also, they are smaller in size and operate generally at 5 to 12 volts DC rather than the bulk, or you can say bulkiness, of the analog components or devices, and requiring higher voltages. All right. The third one is the ease of recording data, the storage and display. So that we are already aware. We have the recording is easier in computers or in hard disks or in the microcontrollers than the analog ones, which could even be in the form of a some basic some traditional recording devices, which are generally unsuitable, or you can say which take a lot of you can say space, or which take a lot of volume of the recording material. But in digital ones, we have seen how things are actually miniaturizing. We have very small pen drives or storage devices which are becoming very small. Even the capacity goes to 64 GB and all those things. So we can say that it's the recording is compact, it's easy, and we can also do a display with these digital devices. And then we can directly, the most important thing is we can directly couple it to the computer. So directly couple to the computer. All right, which is necessary for processing which can be used for interpretation, investigations. And fifth one, you can maybe separately talk about control, a PC based control, which is a direct control. And one of the most important thing is about the noise cancellation, or you can say the advantage in terms of noise resistance. So you can say the noise resistant. So the digital signals generally are actually, you can say, they are sequence dependent. There is some problem with this. I'm getting some lines in this. So there is like it's noise resistant because it's more about sequence dependent, or we can say these signals are coded in the form of zeros and ones. So we have sequence rather than the any arbitrary kind of a voltage or other things. Obviously, they are sequence dependent, but obviously the sequence of ones and zeros that we generally employ, they obviously refer to some voltage, like 1 would refer to 5 volts, 0 would refer to 0 volts. So sometimes if the noise in the the environment, or the noise associated with the external environment is too high, which is actually equal to the digital signal, then we may still encounter some errors. So we may still need to do the you can say filtering and other processes that are required. But obviously digital signal processing, or you can say digital filtering, is generally more efficient and more accurate than and maybe more easier than the analog one. So these are some of the significant advantages with the digital systems that we generally that's why we basically go into the putting up in the AD conversion and DA conversion, because we can do a lot with the signal that we have already taken with from, let's say, we want to measure the strain, we want to measure the we can say we want to measure the acceleration, all those things. So we can do a lot of analysis with those signals when we take them to the computer. So once that conversion is done, we can do a lot of things with that in the computer, like in terms of interpretation, investigations of the data that we have taken, and also we can process it, and we can also use it for online control because we're directly connecting to a PC or a microcontroller. That is one of the significant advantages that we do have with digital signals. So that's why we would prefer this analog to digital conversion. And because most of the sensors, we can say most of the sensors are actually analog output based sensors. We have very few sensors which are actually completely digital in nature in terms of the output. All right. So a typical example, let's say, of an analog signal, suppose we have a signal like this. So this is how an analog signal looks like. So we have some voltage, and we have the time on the x graph, sorry, on the x coordinate in this side. And if we basically want to represent this in the form of a digital signal, what does it mean? It means that rather than having a continuous time in this way, what we have represented as this signal, a bell-shaped curve. So we have specific intervals of time. For example, we have a time instant at this point, which is generally constant, which we call as sampling time. Let's say we have specific intervals of time where we have the signal available rather than continuously having it. All right. So now at this point we have this as the output. At this point we have this as the output. At this point this is the output. So on and so forth. We have different points that we have been able to tap, and then we have something like this. So just completed this way. So what happens is, now for example, we at this instant, when the signals, let's say when the time starts for us in terms of measurement, we don't have any output, for example. So this is the output. Let me take a different color. So this is the output. So there is no output up to this time, but then after reaching to this point we have an output which is equal to this voltage. All right. So then this is held constant. Then we have another value of voltage, and this is again held constant for this sample time. Then we have another value of voltage, then again held constant, something like this, like this. All right, so this is the digital, or you can say digitized, or you can say digitized signal, digital signal, and this black obviously represents the analog part of it. So if you see, let's say अगर आप इसको देखेंगे in different ways से, so एक तरीके से तो ये it is able to reconstruct similar pattern, but what is happening is it's actually losing some of the values in between the sample points. So that's how basically you go into the digital analog to digital conversion, digital to analog conversion. This is how you basically construct it. Now you can reduce this sampling time so that you can avoid losing a lot of data in between. So that can be done, but how much? So can you go almost to a sampling time of, let's say, generally we specify it in terms of sampling time is like, let's say, or you can say sampling time means we can do 1 by sampling time is sampling frequency. So if the sampling frequency is 1 kilohertz, all right, so you can increase it to 10 kilohertz. which means you have 10 times increase the frequency, which means you have reduced it to 10 times, something like this, the timings. So you have divided this into 10 more parts, so you can have more number of values. So you can increase to 100 kilohertz, or you can go to maybe any higher. So how much you can increase, that's the question. So obviously we cannot increase it too much, because increasing the sampling time would mean increased requirement of hardware, and obviously increased requirement of hardware plus additionally we would require increased in terms of memory space, resources and other things, and other issues with the digital electronics at very high frequencies. So obviously we need to strike a trade-off between what should be the sampling frequency of the signal with which we can actually reproduce the best amount of the analog part of the signal. So that's very important in the digital analog to digital and digital to analog conversion. All right, so now how do we do this? We have something called as data acquisition softwares, or you can say data acquisition devices, that we generally that are generally now available in the market. So those actually do this for us automatically in terms of converting a analog signal to digital signal and digital to analog signal. So we do have data acquisitions hardware available from National Instruments, we have from various companies, and we do have a data you can say analog to digital conversion on a microcontroller like Arduino Uno also, because you put in an analog signal, it converts it to a digital signal, but obviously with some limits, like in terms of you have 8-bit signal, you cannot go for more than an 8-bit signal or an 8-bit conversion. So those are the limits. All right, so the question would be how fast sampling can be done. So obviously you can go as fast as you want, but the problem would be requirement of the specialized hardware. So you can say specialized hardware would be required, and maybe larger computer memory. You can say how fast sampling can be done. So that's obviously restricted by these two. So we cannot, let's say for an Arduino Uno, we cannot put it very high sampling, let's say analog digital conversion, because we do not require, for basic applications that we use Arduino for. And for application where we require really, accurate and all those things, accuracy requirement is very high. So obviously we will not use Arduino for those things. We'll use a very specialized microcontroller, a very specialized microprocessor, and which has a capacity to actually, and then memory devices, memory, can say ICs on the board could be taken up. But we do have something called as Shannon's sampling theorem. I'll just write it here. Actually, this theorem tells us for a given signal how much should be the sampling rate for analog to digital conversion. So this is something that can help us actually in striking a right balance. So the theorem says sample the signal at a rate and frequency here would mean the same thing, because it's time dependent, obviously, rate more than 2 times the maximum frequency components in the signal. All right, this will ensure us that we retain all the frequency components of the given input signal. So I hope it's clear to you. So what happens is basically, so for example, we have an analog signal, let's say an arbitrary signal. So it has different frequency components, obviously. So it has a frequency like this. It means this part. Let's say if it's a uniform, it could be non-uniform. So it has one frequency component here. It has another frequency component here, let's say. But it may be quite fast here. So it has another frequency component here. So it has a lot of different frequency components. So obviously it could be an output of any sensor that we are using. So let's say it has a varying amount of frequency components. So we cannot just sample it, let's say at a at an arbitrary sampling rate, where we would like to take points like this. For example, if we take this as the time interval point, this as the sampling point, so and then this as the amount of time that has elapsed. So another point would be here, another would be here, another would be here, another would be somewhere here. But after that, we may not be able to catch the signal properly. We may lose a lot of information. We may lose a lot of the signal characteristics. So this I'll explain properly with another I would say a signal. Let's say signal type like this. Sorry for this poor drawing. So for example, we have a signal like this, which is in this case, let's say uniform, just to illustrate the Shannon's concept in the theorem. So let's say this is the obviously the amplitude, and this is the time. So we have a given analog signal which varies, let's say, uniformly, and obviously has some frequency associated with the signal, given input signal. Now what happens is, if we try to sample it, let's say if we try to take samples of this whole signal at an arbitrary, let's say let's say time, or you can say at an arbitrary frequency, not taking care of the Shannon's concept. So what happens is, suppose we take it this way, some points here, here, maybe somewhere here, another point here, somewhere at this point, at this point. Right. So what we have done is, we have taken some samples here according to this time interval. This way. So because of this, what happens is, if we now take these points to the computer, or to the, let's say, digital device. So if we try to reconstruct this, let's say arbitrary, with some joining these points. This is the type of signal that we are getting. So this blue signal is what we get as an output. Now if you compare this with the original signal, maybe the amplitude is preserved. What's happening? The most important thing is the frequency is lost. The frequency of the input signal is lost. The original frequency is lost, which may be very important for us in terms of measurements. And the second thing is, the pattern that is associated with this is also lost. We're getting a different kind of a signal with a different frequency. Now this thing in digital electronics, or in these systems, is actually known as aliasing, or this is an, can say, alias signal. Because of this, we have not been able to get the right signal. We have got an alias signal, which is actually, we can say this signal is full of errors, and the information that is actually not present. So we have got a different information. So errors and some information which is not actually there. So we're getting a different information. So we're not getting a wrong information actually. All right. So now to take care of this concept, so this thing, so we don't have to say that we will sample it very finely so that we get exactly the same signal. So what we would do is, we would try to do something called as, we have techniques like fast Fourier transform. Sorry, we have Fourier transforms, where we we try to find out the frequency associated with the input signal, and accordingly, if we use a Fourier transform, we will be able to get the frequency components in the signal, and the maximum frequency that is associated with this signal. For example, now this is a uniform one, but you may have a signal which has different frequency components, but the maximum frequency associated with the whole signal actually. So what we will use this concept: sample the signal at a rate more than 2 times the maximum frequency components in the signal. So if we let's say, for example, try to sample this signal with this frequency more than twice than this, so which means, if this is the frequency for this, or this is the time period, and obviously it has some associated frequency, so we have to use the frequency, more than double the frequency of this signal, with which we will be able to construct the right signal back. something like this. All right, so that's why we can write it here. Let's say the fs, which represents the frequency with which we sample, should be more than 2 times the frequency or the maximum frequency associated with the input signal. So if we do this, we will make sure, or we are sure that we will be reconstructing the original signal back. Okay. So there are two things associated with analog to digital conversion. So they are sampling, and second is actually quantization. I'll have to go maybe a little quicker because I have just half an hour left. So sampling, we have discussed that we have to sample it as per the Shannon's theorem. And mind you, this 2f max that we have put in is also called as Nyquist frequency. All right. So any signal that we have from any sensor, now we will have to make sure that we are able to find out the maximum frequency component in that, and then we have to basically use this theorem where we have to sample it twice the maximum frequency component in the signal, and then we'll be able to reproduce the signal correctly. Now it's not just about sampling; it's about quantization also. The quantization talks about the levels, or you can say, converting an analog signal to digital one would require actually the discrete output states that are actually understood by the computer. So quantization would require something called as quantizing and coding. All right. So here quantizing is again converting an analog signal to digital states. Coding would refer to putting up a digital code, or you can say assigning a digital code, or you can say code word or a number to the digital states that we have got, or consider the output states. So now it's similar to something like this. So you have a signal, for example, which varies linearly like this. So you can convert maybe the maximum, let's say the maximum value is 10 volts, the minimum is obviously 0 volts. So now we have seen that we can sample it at any instant, or maybe as per the Nyquist frequency or the Shannon's theorem. But what are the states? Can we just arbitrarily take any state, or do we have to convert it to a particular, let's say basic, some of the requirements as per the digital electronics? So we have something called as coding. So we do have something called as levels, quantizing levels. Let's say if this is the level, the next level is similar to this. So these levels are obviously at a constant, let's say height. They cannot be arbitrary. All right. So now if we have sampled it here, so this part, how do we do this? Or if we have sampled it here, how we do this? So obviously it means that we have a level that is associated with this or this. So we have to choose this or this. So for example, if we sample it here, it may be that we have to choose this as the level. And if we have sampled here, we may have to just choose this as the level. All right. So this thing happens. We do have digital numbers. So there is a dependency again on the hardware. So what we have something called as, I'll just maybe draw it here, the table. See, this may not be really clear to you, but if you are interested in understanding it, I can maybe discuss it again, maybe later. But this is just to give you more, feeling of what actually happens inside the systems. So this is we have some digital values like 0, 0, 0. So this means 3-bit. So we have a 3-bit A to D converter, analog to digital converter, or you can say a quantizer. So we have 0, 0, 1 that we have seen in digital electronics. Then we have 0, 1, 0. So this is how the digital electronic moves, these binary systems. So 0, 1, 1. Then we have 1, 0, 0. Then we have 1, 0, 1, 1, 1, 0. Then we have 1, 1, 1. So we have 1, 2, 3, 4, 5, 6, 7, 8 states. So corresponding to you can say 3-bit, quantizer, we have 8 states, and we can refer them by even the decimal values 0, 1, 2, 3, 4, 5, 6, and 7. All right. Now, for a 10 volt, let's say, signal that we had got, so we need to obviously divide this into some, again here in terms of, let's say, 8 bits. So 1, 2, 3, 4, 5, 6, 7, and 8. Now this would mean something like this. I'll just maybe try to draw it properly. So 1. Let's try to understand this slowly, because this may not be really clear at the first instant. So let's say the original signal was this green one, and this is the digital signal. Now we're not talking about sampling here, we're just talking about quantization. How do we code this? How do we convert this into a digital state, and then how do we code it properly? So this is the coding that we have used for a, let's say, 3-bit maybe quantizer. Now, because this is 10 volts, so obviously this has to be something like 10, but what does it refer in terms of voltage? So if we divide 10, let's say we have 10, and we divide it into, we have 3 bits, so 2 to the power of 3 is 8. So 10 by 8 would be 1.25 volts. So that means each bit actually would give us a 1.25 level. So we have 1.25, 1.25 means 2.5, 3.75, so become 5, 5, then obviously 6.25, then we have 6.57, we have 8.25, 8.75, and then we go to 10. So obviously we write here as 0 to 1.25 volts. This refers to 1.25 to 2.5 volts. This refers to 2.5 to 3.75 volts. 3.75 to 5 volts. This is 5 to 6.25. This is 6.25 to 7.5. 7.5 to 8.75. 8.75 to 10 volts. So this means that with this 3-bit quantizing technique, we have been able to actually divide this 10 volts into this type of 8 states. So we can represent a 10-volt signal from in the analog signal in terms of 8 states, but each state would give us a 1.25 voltage of increment. What it means is that if we have, for example, a 6 point, let's say 25, so that we obviously means that it's somewhere here. But if we have 6 point maybe 3, all right, so this doesn't mean 1.25 of resolution. So we do have errors. Obviously we do not have an exact value of the digital signal corresponding to that an analog voltage. So we do have these errors. These are called as quantizing errors. And obviously this can be improved by improving the number of bits. So we can have 8-bit AD converters, or we can have 16-bit AD converters. We have 32-bit AD converters. So all those things actually would increase the values, the cost associated with these conversions. All right, so if we do have let's say a voltage of 10 volts again, but if we use an 8-bit converter, so we have 2 raised power 8 bits, so we have 2 raised power 8, which means a very high value. So we do have, if we do this, 2 raised power, it's 2 to the 4 to the 8 to the 16 to the 32 to the 64 to the 128 to 56. So it's 10 by 256, which is roughly maybe if it's 100, it's like maybe 0.05 approximately volts. So we have very good resolution. So that means even a 0.05 value like this, where it is a 0.05 value, we can represent it by a digital signal. And similarly, if we go for a, let's say 16-bit, so we do obviously have a very high resolution device, obviously, but 16-bit and these AD converters and all those things may become expensive, but we do have those things readily available. All right. Is there any query? Zubair, are you there or you are sleeping? अच्छा, क्या सर के ऊपर से तो नहीं जा रहा? ये मैं लिख रहा हूँ, यही नोट्स हैं मेरे पास, तो यही है, थोड़े से मैंने रफली लिखे हैं. ये भी सेव हो जाएगा, जो मैं यहाँ लिख रहा हूँ वो सेव हो रहा है एज पर माई स्क्रॉलिंग. एनी अदर स्टूडेंट हैज एनी डाउट? कोई एक बोलो, या तो कुछ सो रहे हैं सब लोग सुबह सुबह. ठीक है. सो the process of AD conversion now starts with, obviously we'll make it block diagram form. So sensor output, then we do have something called as a buffer amplifier, then we have low pass filter, we have something called as sample and hold circuit, or you can say we have the AD conversion, and obviously it goes to computer or memory. So it may be like a sensor signal generally is very low in amplitude, and we may do an amplification of the signal with a buffer amplifier. Then we will try to filter out the high frequency components from this. We'll allow only, let's say, low frequency components. Then we have something called a sample and hold, which is an important circuit in AD conversions. Then obviously AD conversion takes place, which is like, in terms of a digital signal we get as an output, and then it goes to the computer memory. So we have a buffer amplifier actually that tries to amplify the signal without actually putting up the load back on the sensor. That's why we call it buffer amplifier. It amplifies the signal because the sensor output from any sensor that you may have seen, that we generally use a MEMS based sensor, and all those sensors, they are generally very low voltage signals. They may be even in terms of millivolts or sometimes less than that. So we need to amplify these signals to properly take them to the for AD conversion and putting them to the computer, because we generally operate at 5 volts digital signals or 3.3 volts. So that's why an amplification is required at the first instance. Then sometimes, because there are we know that it's a, let's say, low frequency application, so we may directly go for a low pass filter, where we will try to filter out the high frequency component which may be associated due to noise. So we'll have only the low frequency components. And then we have a sample and hold operation that is required in AD conversion. You don't need to go deeply into this. Then this process of AD conversion that we have just talked about is takes place, and then it's taken to the computer memory, where we analyze the signals. All right. Now let's talk about the circuit part of AD converter and then DA converter. I'll just move to the yes. सैंपल एंड होल्ड बेसिकली क्या होता है, ये मैं आपको इसमें बताऊंगा. ये है आपका एनालॉग टू डिजिटल कन्वर्जन. ये बेसिकली एक ऑप एम्प जैसा होता है. ठीक है, एक सेकंड. ये ऑपरेशन एम्पलीफायर एक सर्किट होता है बेसिकली. ये जब हमने इसमें एनालॉग टू डिजिटल कन्वर्जन किया ना, फॉर एग्जांपल इसमें दिखाऊंगा आपको क्वांटाइजेशन. देखो यहाँ पर जैसे अगर आपकी सिग्नल इस तरह थी ना, स्ट्रेट लाइन दिख रहा है आपको, तो ये सिग्नल जैसे यहाँ पर आपको एक जूम करके दिखाऊंगा. बेसिकली जैसे यहाँ पर आपकी सिग्नल थी ग्रीन कलर की, ठीक है. तो अब आपने इसको क्या किया, आपने कहा इसके बदले जी मैं ये वैल्यू रखता हूँ कांस्टेंट वैल्यू, बिकॉज मेरा रेजोल्यूशन इतना ही है, तो मैं ये कांस्टेंट वैल्यू रखता हूँ इस दौरान. ठीक है, तो ये सैंपल तो हो गया, जैसे सैम्पलर ने सैंपल किया, लेकिन इसको होल्ड भी करना है जब तक डीए कन्वर्जन इस वैल्यू को फिर से कन्वर्ट करेगा ना, फॉर एग्जांपल जो ये प्रोसेस है कन्वर्जन वगैरह, तब तक ये होल्ड करता है इस वैल्यू को। ये जो है ना, इसको कहते हैं होल्ड, ये वाला, ठीक है। ये बहुत ही कम होता है, मतलब ना ये वैल्यूज, मतलब ये नहीं कि इतना होल्ड है। बेसिकली डीए कन्वर्जन एडी कन्वर्जन है ना, बेसिकली इट टेक्स सम टाइम एक्चुअली टू डू दीज थिंग्स, जैसे सैम्पलिंग है या इस तरह की चीज, सॉरी सैम्पलिंग है, इस तरह की चीजें, इट टेक्स सम फाइनाइट अमाउंट ऑफ टाइम व्हिच मे बी इन माइक्रोसेकंड मिली सेकंड्स, बट फॉर दैट पीरियड ऑल्सो यू नीड टू होल्ड दिस। समझ रहे हैं आप? ये एक मतलब समझिए आप, ये बेसिकली एक या तो ऑप एम्प जैसा हो सकता है या फ्लिप फ्लॉप जैसा। आपने फ्लिप फ्लॉप पढ़े हैं? अच्छा, वो डिजिटल इलेक्ट्रॉनिक्स में हम पढ़ते हैं फ्लिप फ्लॉप। उसमें क्या होता है, बेसिकली जो इनपुट स्टेट होता है ना, वो आउटपुट स्टेट वही रहती है जब तक हम इनपुट पे चेंज ना करें। समझ रहे हैं आप? तो अगर इनपुट पे चेंज होगा तभी आउटपुट पे रिफ्लेक्ट होगा, वरना क्या करेगा, तब तक वो रिटेन करेगा रजिस्टर जैसा। समझ रहे हो? So it holds that, it has a finite value that time, otherwise it doesn't know what to keep. So if you ask him to keep this and then forward it, so what you tell him that unless you process the other signal part, जिसको जो करना है, बिकॉज सिग्नल तो बहुत ही रैंडम भी हो सकती है, उसको प्रोसेस करना है, उसकी वैल्यूज क्या है, उसकी डिजिटल वैल्यूज क्या है, वो सब कन्वर्जन करना है। So till that very finite amount of, which is generally in very, these days it's in microseconds, I would say, or milliseconds, microseconds probably. So till that time, it has to hold that value. So that's why you call it sample and hold. It's nothing but an op amp actually. Op amp circuit है, इसमें resistor और capacitor लगे होते हैं. It keeps on the value of that sample signal until the next signal comes in. ठीक है? तो ये आप बुक से भी देख सकते हैं, और फर्दर इसमें थोड़ा डिटेल में जाएंगे तो थोड़ा सा और कॉम्प्लिकेट हो जाएगा। मैं इसलिए इसको चाह रहा था कट शॉर्ट करना इस वक्त। तो ये हमारा सर्किट है डिजिटल टू एनालॉग कन्वर्जन का, और ये हमारा है, ये मैंने बुक से लिया है आपके, ये बेकविथ की बुक है। दिस इज ए डिजिटल टू एनालॉग, दिस इज एन एडी कन्वर्टर, एनालॉग टू डिजिटल कन्वर्टर, और ये है डिजिटल टू एनालॉग कन्वर्टर। ठीक है, तो मैं इसको एक्सप्लेन करूंगा आपको थोड़ा सा, होता कैसे है बेसिकली। तो हमारे पास ये एक रेफरेंस वोल्टेज होती है, ठीक है, वी हैव ए रेफरेंस वोल्टेज which is generally, let's say, 1 volt in these type of systems, and we have some solid state switches, or you can say gate। solid state switch क्या होता है, जरा आप बताओ। अभी कौन क्वेश्चन पूछ रहा था? क्या नाम है आपका? हाँ, खबर, जो आवाज से पहचान लिया मैंने। सॉलिड स्टेट स्विच क्या होता है? हाँ, इट कुड बी लॉजिक गेट्स, और इट कुड बी इवन दीज सेमीकंडक्टर बेस्ड, जो हमारे ये होते हैं ना, क्या बोलते हैं, ट्रांजिस्टर्स या इस तरह के डायोड, ये सारे स्विचेस होते हैं। ठीक है, यानी अगर हम बेस की वैल्यू पे कुछ करंट डालेंगे तब वो ऑन हो जाएगा, बायस हो जाएगा, और अगर उससे कम डालेंगे तो अनबायस रहेगा। ठीक है, so transistors act as switches for us, so let's say there are some transistors attached। अब हमारा डिजिटल टू एनालॉग कन्वर्जन है, फॉर एग्जांपल मैं एक्सप्लेन करूंगा। तो डिजिटल टू एनालॉग में क्या, हमारे पास डिजिटल सिग्नल है, उसको हमें एनालॉग में कन्वर्ट करना है, फॉर एग्जांपल। ठीक है, तो डिजिटल मींस वी हैव सम स्टेट वैल्यूज, लेट्स से 0 1 0, अगर 3 बिट है तो इस तरह है, या 8 बिट है तो हमारा कुछ हो सकता है इस तरह हो, है ना। अब ये चीज क्या रिप्रेजेंट करता है, दिस रिप्रेजेंट्स सम states, let's say high state, low state, high state, low state, isn't it? So in this case, this talks about an 8 bit, so we can have only 3 bit also, 4 bit, 5 bit, 6 bit, but generally हमारा 2 raised power of उस फॉर्म में होता है, या 3 भी होता है, 4 भी हो सकते हैं। So it depends on the type of resistor and the type of resolution that we would like to get actually। Now ये सारी चीजें जो मैंने अब आपको दिखाई, जैसे बफर, एम्पलीफायर, फिल्टर वगैरह, ये सारी चीजें आज एक इंटीग्रेटेड सर्किट है ना, आईसी पे एक सारी चीज ना, सारी चीजें एक हम फैब्रिकेट कर सकते हैं। तो इसीलिए हमारे पास एक छोटी सी आईसी आजकल आती है, एडी कन्वर्जन की या डीए कन्वर्जन की, समझ रहे हो आप? तो हम उसमें डाल देते हैं, तो वो ऑटोमेटिकली हमारे पास जो भी रेजोल्यूशन जो उसका दिया होगा वैल्यू, जैसे 8 बिट होगा, 4 जैसे होगा, ठीक है, 16 बिट होगा, वो हमें ऑटोमेटिकली वो वैल्यूज दे देगा। समझ रहे हैं आप? बट तब भी थोड़ा सा पता होना चाहिए अंदर क्या हो रहा है। So this is the, let's say, there are different ways, and in fact I'll tell you there are different ways to do this digital to analog and analog to digital conversion, but we'll just stick to this one. We don't have to go much into that, but we just, it just gives us some flavor कि मतलब करते कैसे हैं ये सब। तो इसमें क्या होता है, जैसे हमारे पास 8 gates हैं 0 1 2 3 4 5 6 7, so which obviously represents 8 bits. Now with this type of the digital to analog converter, we can convert an 8-bit signal or an 8-bit digital signal to an analog output. ठीक है, समझ रहे हैं? तो अब 0 1 2 3 4 5 6 7 ये तो ऑब्वियसली हमारा आएगा पीसी से या माइक्रो कंट्रोलर से, बिकॉज डिजिटल टू एनालॉग कन्वर्जन होगा माइक्रो कंट्रोलर से ही, because that we have to output to the actuator, isn't it? So in this case what happens is, for example, we want to give this as the output 0 1 0 1 triple 0 and 1 1. So maybe an analog device or an analog actuator may not be able to understand this language, isn't it? So we need to give it in the form of an appropriate voltage. So what does this represent in terms of voltage? Fine. So we use this type of circuit. So in this we use some resistors, let's say 1R, 2R, 4R, 8R. What it represents is the value of the resistor used here. So this is nothing but resistance, let's say R, you have used some value of resistance R, okay, which is in the form of ohms. So यहाँ 2R means 2 times that resistance. So if this is 1 ohm, this will be 2 ohms, and this is 4 ohms because it's 2 raised power of 0, 2 raised power of 1, 2 raised power of 2 in the form of, okay, these bits. So 2 raised power of 3, 2 raised power of 4, and similarly up to here. So what happens is, for example, if there is a signal like maybe 0 bit pe signal high hai, which is the least significant bit, then we have all zeros. So 1 2 3 4 5 6 7 8. All right. So this would mean just one, isn't it, least significant bit. So this means obviously अगर हम देखें भी ये इसका मतलब बहुत कम voltage है, isn't it? Output है या current output है हमारा. So what happens is, because of this one, this gets connected. ठीक है? There is some reference voltage, for example 1 volt or whatever we want to give in terms of digital signals. So this will be divided by, because this will act as a voltage divider, isn't it? So इस वजह से क्या होगा, हमारी करंट क्या जाएगी आगे, E reference क्या हो रहा है, divided by 128 R, isn't it? इसका मतलब बहुत ही कम करंट जाएगी, इसका मतलब बहुत ही कम करंट जाएगी to the op amp. It's an op amp here, an inverting amplifier, operation amplifier. ठीक है? And with appropriate values of, let's say, RG, we can amplify that signal also, because if we want to amplify, and then it will output some voltage here, isn't it? So this will go to the actuator. समझ में आ रहा है? अगर हमारे पास ये है 7 हमारे पास हाई है, तो 1 0 0 3 4 5 6 7 8. It means it's a quite high signal, but not really full signal, because we have other values as other states as low. So it means E reference जो भी हमारी है divided by just 1 R, isn't it? So this will mean quite high current, isn't it? So this will flow through this, and obviously we'll have a good amount of output. समझ रहे हैं? हाँ, तो इसी तरह for any state, let's say 1, for example, we have 1 0 1 0 0 0 1 1 2 3 4 5 6 7 0. इसका क्या मतलब होगा? इसका मतलब होगा 7 switch is closed. So I will try it with this. Switch number 7 is closed, switch number 5 is closed, switch number 1 is closed. So which means if we add all these three, so what it means is that we have this one, these all three are in parallel, isn't it? So ये तीन resistors parallel में है, तो इनका हम resistors का वो जो है equivalent resistance निकालेंगे, और इसी हिसाब से हमारी जो यहाँ पर current flow करेगी. समझ रहे हैं आप? So accordingly we actually are dividing this whole digital signal in values that we have from the input into some voltage that gets amplified. So we can accordingly amplify. We can use an inverting circuit again to get it back to the right signal that we have seen, and this way the digital to analog takes place, conversion. अब इसमें बताओ पहले कोई किसी को डाउट है? हो सकता है डाउट से ज्यादा क्लियर हो. बोलो बोलो. ये वाला जी, ठीक. 1 आप समझो क्लोज्ड है, तो ये हमारा यहाँ पर है ये हमारा 7 है, ये 6 है, ये 5 है, ये 4 3 2 1 0 बिट। यहाँ पर स्विचेस हैं, ये स्विच है और ये हमारे स्टेट्स हैं। ठीक है, स्विच नंबर 7 जो है वो स्टेट 1 में है, इसका मतलब वो हाई है, इसका मतलब वो क्लोज्ड है। स्विच नंबर 5 भी क्लोज्ड है, स्विच नंबर 1 भी क्लोज्ड है। जब ये तीन स्विचेस क्लोज होंगे तो इनके अनुसार यहाँ पर जो रेजिस्टेंस आएगी ना, यहाँ पर ये तीन ही रेजिस्टेंस एक्टिव हो रहे हैं ना, तो इन्हीं की हम इक्विवेलेंट रेजिस्टेंस निकाल के टोटल वोल्टेज देखेंगे कितनी, ठीक है, हिल रही है, जो टोटल करंट कितनी फ्लो हो रही है, उसी हिसाब से आउटपुट हमें मिलेगा। आया समझ? और बताओ, और किसी को इसमें डाउट है? So we basically require four basic elements. You can just maybe list it like this only. So reference voltage, like this is one. Second is a ladder arrangement of resistors, which obviously vary in the form of 2 raised power of 0 to 2 raised power of 7 here for 8 bits. If we have a 3-bit digital to analog, we will have only 3 resistors here. And the third one would be solid state switches, which are these. Okay, so this could be simple, maybe जैसे कहा logic gates and maybe other transistors, it could be there. And the fourth one is the op amp circuitry. So we require 1, 2, 3 and 4 components for a digital to analog conversion. ठीक है? Now similarly we have analog to digital conversion. So this is the last part here. बस ये लास्ट पार्ट है, इसको देख लो तो ये फिनिश हो जाएगा। हनीफ सर वेट कर रहे हैं, चलो मैं एक मिनट में इसको बताता हूँ, आप देख लो। सो एनालॉग टू डिजिटल कन्वर्जन में क्या हमारे पास भी एक और ई रेफरेंस, हमें या हम कहते हैं वोल्टेज रेफरेंस चाहिए हमारे पास। हमें यहाँ पर वोल्टेज कंपेरेटर चाहिए। अगर आपने ऑप एम्प्स में हमने जब पढ़ाया था, उसमें कंपेरेटर्स एक चीज होता है, उसमें क्या होता है, आउटपुट हाई या लो होता है। वोल्टेज कंपेरेटर्स में हर वक्त आउटपुट क्या होता है, हाई और लो। ठीक है, यानी 1 और 0 रादर देन द अदर ऑप एम्प्स। ये भी ऑप एम्प ही है, लेकिन ये कंपेरेटर वाला ऑप एम्प है। इसमें क्या होता है, इसमें जो रेफरेंस वोल्टेज होती है उस हिसाब से अगर यहाँ हाई या लो होगा, उसी हिसाब से स्टेट यहाँ पर या 1 होगी या 0 होगी। 1 या 0 या 0 या 1 आप जैसे लिखना चाहें। सो इट कैनॉट हैव एनी अदर वैल्यू रादर देन हाई और लो, व्हाटएवर। ठीक है, सो यहाँ पर हमारे रेफरेंस वोल्टेज चाहिए, वोल्टेज कंपेरेटर्स चाहिए, एक बाइनरी एनकोडर इसमें एक स्पेशल चाहिए होता है, एक इलेक्ट्रॉनिक सर्किट है अगेन। ठीक है, और हमारे पास जो ऑब्वियसली रेजिस्टर्स चाहिए हमें, सेम रेजिस्टर्स चाहिए हमें। लेकिन इस सर्किटरी में आप एक चीज देखेंगे, ये सिर्फ 3 बिट एनकोडर है, या इसको हम कह सकते हैं 3 बिट ए टू डी कन्वर्टर है। 3 बिट में हमें चाहिए होता है अकॉर्डिंग टू 2 raised power of 3, इसमें थोड़ा रिवर्स होता है। सो दिस इज 8, so we require 8, 1 2 3 4 5 6 7 8 registers and 1 2 3 4 5 6 7 comparators। ठीक है, so we basically क्या है, हमारे पास एनालॉग सिग्नल जो आती है इसमें एज एन इनपुट, ठीक है, वो कंपेयर होती है इस रेफरेंस के साथ, लेकिन अकॉर्डिंग टू द वैल्यू ऑफ द एनालॉग सिग्नल वो रेफरेंस के साथ कंपेयर होती है। अगर वो हाई सिग्नल अगर बहुत ही हाई होगी फॉर एग्जांपल, तो रेफरेंस जो यहाँ तक पहुंचेगी, जैसे क्योंकि ये वोल्टेज डिवाइडिंग सर्किट है, सारे रेजिस्टर्स की वजह से क्या हो रहा है, वोल्टेज ड्रॉप हो रहा है, तो उसी हिसाब से जहाँ यहाँ पर कंपैरिजन होगा, यहाँ पर कंपैरिजन होगा, यहाँ पर कंपैरिजन होगा, हर जगह इस एनालॉग सिग्नल के साथ कंपेयर होगा जो है ये रेफरेंस का वोल्टेज डिवाइड होकर। तो उसी हिसाब से जो भी हमारी एनालॉग सिग्नल अगर बहुत ही कम है वैल्यू, जिसको हम कहेंगे बहुत ही लो वोल्टेज है हमारी इनपुट, तो उसी हिसाब से ये कंपैरिजन में बिट्स उसी हिसाब से दे देगा। तो यहाँ पर बिट्स जनरेट होंगे 1 0 1 0 1 0। तो उसमें एक बाइनरी एनकोडर हम यूज करते हैं, बेसिकली वो उस एनकोडिंग स्कीम एक होती है, इसको आपको देखने की जरूरत नहीं, आप बस इतना याद रखो, एक बाइनरी एनकोडर होता है विच कैन एनकोड दीज टू एक्चुअली दिस फॉर्म। जैसे फॉर एग्जांपल हमारे पास इसमें कोई कॉम्बिनेशन आ गई, उसको ये फाइनली 3 वैल्यूज में आपको दे देगा। फॉर एग्जांपल अगर आपका 0 1 0 आउटपुट दे देगा, तो ये होगा हमारा 2, और 0 0 1 होगा तो ये 1 होगा। ठीक है, और 1 0 0 होगा ये 4। ठीक है, सो दिस इज हाउ यू विल get in this form. So the only question is binary encoder. You can look further into the books what this actually is composed of. This is nothing but a kind of a small circuitry, again form of logic gates, which tries to compare these values and then gets values of the binary output from here. So you get a 3-bit output from here corresponding to these 7 आउटपुट स्टेट्स. ठीक है, वो बहुत ही आसान एक सर्किट होता है, वो आप देख सकते हैं किसी भी डिजिटल इलेक्ट्रॉनिक बुक में इफ यू आर इंटरेस्टेड. अदरवाइज यू कैन जस्ट से दैट देयर इज अ बाइनरी एनकोडर दैट कन्वर्ट्स दीज कॉम्बिनेशंस टू द बाइनरी स्टेट्स 0 1 0 1 0 0 1 1. इसी तरह जब हमारे पास 8 बिट एडी कन्वर्टर होगा तो उसमें 2 रेज़ पावर ऑफ 8 हमारे पास रजिस्टर्स और ये -1 करके हमारे पास कंपेरेटर्स होने चाहिए, तब हम जो है. तो इसी तरह कॉस्ट इनका बढ़ता है अकॉर्डिंगली, लेकिन जब हमारी हाई एक्यूरेट रिक्वायरमेंट्स होती हैं तो उस वक्त हम ये कॉस्ट देखते नहीं है, और ये सारी चीजें आज हम फैब्रिकेट कर सकते हैं एक सिंगल इंटीग्रेटेड सर्किट के ऊपर. ठीक है, सो आई थिंक दिस इज एनफ for you to understand what basically AD and DA converter actually is doing and what actually how they are manufactured. There are and you should mind in that there are several other techniques also to used for doing this AD and DA conversions. I think this is enough for this part. We'll start with module 3, which is about dimensions, maybe in motion and maybe force measurements. We'll cover topics specifically rather than going in details because I have listed out some of the topics. Accordingly हम जो है उन टॉपिक्स पे ही डिस्कशन करेंगे और उसको हम कवर कर लेंगे. ठीक है.